Good morning, everyone. My name is Nyame Kolisa. I'm a senior researcher or technologist at the HPC. So today, I'll be giving you guys a walkthrough on how we plan to enable our users to leverage cloud, HPC, and quantum computing resources, and what we anticipate the expected workflow should look like. So maybe a good point to start would be, why are we interested in quantum computing right now? So if you look at the expenditure for this year in terms of investment into quantum computing, South Africa is sitting at around 54 million that's been invested so far, which is a lot of money in South Africa terms. But if you look over at China and they're spending $15 billion, or over to America, the Americas, just Canada alone, is $1 billion as well. The UK is spending $4 billion. There's considerable sums being invested into quantum computing, and unfortunately, we're falling by the wayside. And the scary part about this graph over here is that we don't even know the companies that haven't disclosed. So this is just the public information that's available to us that gives us a sense that there's huge, massive investments into quantum computing, and we need to find a way to leverage all the hype. It's not just hype, but I mean, it's the implications of us not keeping abreast of the developments means that we're going to fall even further behind economically. So if we take into account Moore's law, and we think back to these massive mainframes that were used to develop the space program, right? If you consider the lunar guidance systems in Apollo and the atomic program, the atomic bomb program, it's these old mainframes from the early 19th century were built of these transistors, and when you compare them to machines of today, like what you're wearing on your wrist or the laptop in front of you, it's the orders of hundreds of thousands, if not millions of times more powerful than those systems that took man to the moon and devastated humanity. So a place to try and explain quantum computing to those that may not be familiar with it is, let's start with how a typical PC works today. So integrated circuits, they use these things called transistors and logic gates. So very simply put, they process information in bits called ones and zeros. A quantum computer, on the other hand, it has something special that's known as a qubit. So the qubit has various properties that exploits the quantum nature of the universe. So a qubit, the states of a qubit can be in the superposition, and instead of being just a simple 0 or a 1, as in classical bits, they can be in the superposition, where they're both 0 and 1 concurrently. And any measurement of the superposition state gives you a probability of measuring the 1 or a 0. So to give a simple example and to avoid complication, let's take a student who applies for either a conference overseas, or in the case of working adults, let's say that you apply for a promotion or a bonus increase. So take the letter that you've submitted. When it comes back in the mail, let's say that it could be accepted or it could be rejected. This is what we call a superposition. The process of that letter being routed through a mailing system and going through all these different mailing boxes, that's equivalent to quantum gate operations. So you can think of this letter that's now in this superposition state, traveling through all these different gates as a quantum circuit. A quantum circuit is a quantum algorithm that allows us to exploit the quantum nature of the universe to have increased processing performance. Finally, after you have your superposition state, you put this through a quantum circuit or a quantum algorithm, you have a measurement. Now, that measurement is the process of opening the letter. It could either be an accept or a reject. But what you want to do is you want to try and bias it, obviously, to be accept in the case of traveling or a promotion. So you use physical properties of entanglement and interference to suppress the chances of that letter being a reject and to inflate the chances of that letter being an accept. So some of the applications where we think that we're going to see a huge improvement or scale up in compute with quantum computers is, one of the biggest ones is Shor's algorithm. This is a factorization problem. So everything that you use today, from banking to computer security to encryption, That is used by the calculation or determination of prime numbers. So too is the Bitcoin nonce calculation from Bitcoin mining and crypto minings. So this is quite important when you see the investments or the increase in stock in crypto ever since Trump has won the election and being backed by Elon Musk and their plans for the whole crypto Tesla facilities across the United States is we've now seen that the increase in Bitcoin has gone from hundreds of thousands to tens of thousands of dollars a few years ago. Rands, and now we're looking at 2 million rands before the close of the year. So quantum computing, in terms of optimization and factorization problems in finance, in banking, and security, this is going to be a place where QC plays a massive, massive role. Similarly, as for prevalent for AI, machine learning, and generative AI, quantum computing can scale up these processes and we can reap huge benefits and gains from applying quantum computing. Another application which is really good for CHPC users is quantum chemistry and drug discovery. As South Africa, we are unfortunately faced with a number of health pandemics and drug discovery and coming up with cures and identifying unique cases for our South African context to these problems is going to be pivotal. And quantum computing is a way that we can leverage technology to solve problems that are very specific to us and are impacting and affecting us. Another one is we have an energy crisis right now. So material sciences is another big domain at the HPC. With quantum computing, we can actually discover materials more efficiently than you could on traditional classical HPC compute. And I mean, intrinsically, in nature, there are fundamentally quantum problems from the grand, like black holes. We still don't have a unified theory to go from quantum to the grand scale of the universe, all the way down to the microscopic. Phenomena that is intrinsically quantum in nature will benefit from quantum computing. So we've established that there's a use case and there's a need for quantum computing. So what's the workflow going to look like for a typical researcher that's interested in quantum? So at the CHPC, what we want to do is make available to you the Saboa OpenStack Cloud. David's discussed at length about this. And one of the benefits that this has is that the typical use case of a user, they'll install something on their laptop, they'll run it, eventually they'll reach a peak where they either run out of memory or they run out of CPU and they can't complete their problem. It becomes NP complete on their particular use case. So they can come onto Saboa, and over there we have images and CPUs and RAM that will allow you to scale your problem up and find solutions to bigger and bigger problems. What we also are doing is we're providing pre-built or pre-baked images for a number of popular frameworks that are used throughout the world, Qiskit, Penny Lane, Torch Quantum, TensorFlow Quantum. So what we want to do is develop an ecosystem where quantum users can come onto Saboa, they can use it as a sandbox or a playground to vet and verify that the quantum gates and the quantum circuits are in fact actually working correctly before they scale that up onto the cluster or a GPU cluster or an actual quantum device. So just going in order of magnitude of cost, it's cheaper to prototype something in the cloud than it is to do that on HPC, than it is to do that on an HPC GPU environment, than it is to do on an actual quantum device. The hours that we're going to have on a quantum computing device are very limited and very expensive. So we want to make sure that users of our facilities and all our resources, they prototype on the cheapest one, refine, and make sure that they can actually scale up adequately. So a typical quantum computing user, they'll log into the OpenStack interface. We'll encourage them to make use of GitOps and just make sure that they version control everything. Understandably, like in a competitive research environment, people don't want to be open with their research. There's nothing stopping you from having a private Git-like repository. And then after that, what we have as well baked into the images is you can locally remote into a Jupyter lab, if that's your comfortable environment, and making use of Python virtual environments to make sure that all your information is self-contained and can be easily shared, that you back that environment back up into GitHub and share it with your colleagues, and once you've published, share it with your peers as well. For those of us that are more technically inclined, you can also make use of some of the advanced features of OpenStack that involves Ansible, Terraform, and Circle CI. So what that does is allows you to preserve your infrastructure as code on GitHub, and whenever you make changes, you'll trigger Circle CI continuous integration prompts that will then check and test against all your infrastructure if it's still valid or not. And this is very important for some of the frameworks like Qiskit, because what they do is that they deprecate and change almost arbitrarily their entire software stack very, very frequently. So you need to have a framework where you're consistently ensuring that the code that you're providing to users or the infrastructure that you're provisioning for the QC users is always up to date and actually reliable and works. So I've put this picture in here as just to emphasize the fact that it's absolutely critical that users of our QC infrastructure understand that their problem and their use case has been adequately scaled and works sufficiently on the resources that they're targeting. We have oftentimes at the CHPC users requesting GPU nodes or GPU resources, and they haven't adequately scaled their problems to make use of the entire facility or the entire quota that they've requested. This will be a catastrophe for quantum computing. If the user doesn't understand how to scale their problem adequately and isn't making full use of what they requested, they're going to waste our access. And as I said, it's an expensive resource and limited one. So the OpenStack Cloud is a sandbox. Think of it as a place where your laptop or your personal computer or your personal machine doesn't cut it anymore, and now you need an environment where you can experiment and test and see how far you can push the research that you're trying to do. Now, scaling up from the cloud is we then go to HPC. So I'm not sure if everyone in the audience is familiar with HPC, but effectively, if you take your laptop and you scale that up to an enterprise server, you have that over there. You put lots of these together, and you have a cluster. You put these in a rack, and you have many racks. You have a data center. So the key thing in HPC is the interconnect. So at the center there, you have a switch, and in between that, you have a high-performance network. This will be InfiniBand in this case. At the CHPC, we have Lengao. It's Cheetah in Setswana. So this was deployed, launched in 2016. It was the first petascale cluster on the continent. We were on the top 500 at a time. There's over 1,500 nodes at the CHPC's data center. We have fat nodes as well. We have GPU nodes. So this is what's interesting for quantum computing, because it's the GPUs and the NVIDIA's Q-Quantum SDK that allows us to exploit these larger and larger number of qubits and gate arrays. The problem with the current Lengao cluster is that the V100s that are in the production, they only go up to 16 gigs and 32 gigs, which is too small for the current quantum problems that we'd like to solve and the future ones that are going to be presented to us in the future. So there's also a parallel file system that you need for a data center, and we have a InfiniBand high-speed interconnect, and obviously a scheduler. So the other constraints that you have with a data center is that you have to conform to whatever's available on the cluster. So with Python, it's quite easy. You can deploy a lot of things locally and just have them in a virtual environment, and you're good to go. The freedom that you have with, at least with cloud, is that you can orchestrate or configure your environment as you see fit, or as your provider can do that for you. Yeah. So what is in the pipelines is hopefully an NVIDIA A100 GPU upgrade. But as David has alluded to, he anticipates that there could also be a deployment of that infrastructure in the cloud, in which case then we skip the step of going to HPC and we deploy these quantum images in the cloud directly for experimentation. And Mervyn will need to give us a new name, but we have the new 4 petaflop cluster coming up as well. So it's going to be exciting to see what we can do in terms of quantum on there as well before we go directly to quantum devices. Okay, but I mean, the workflow stays the same. You're going to keep your software, you're going to keep everything that you need provisioned in GitHub. And then on top of that, you'll make it easy or redeployable using Python virtual environments. You'll sanitize your different environments. You'll have one for Penny Lane, another one for Qiskit, and another one for TensorFlow, and even multiple ones for the same SDK. Okay, so what is Penny Lane? So Penny Lane is from a company out in Canada, Xanadu. So this is a quantum computing SDK, and they focus on quantum machine learning, quantum chemistry, and optimization problems. So interestingly enough, one of Francesco Petriccioni's former students, Maria Schilds, She was at UKZN, and she's one of the founders of Penny Lane in Canada. So early this year, the really smart guys over at Xanadu, they published a paper, Hybrid Quantum Programming with Penny Lane Lightning on HPC Platforms. So this was a stroke of genius, because what they want to do, they want to corner the markets and say to everyone, we have an SDK and a framework that can work on HPC, it can work on CPU cores, it can scale across GPU clusters, it can scale across large HPC systems. And when I came across this, what we did then is we incorporated this Penny Lane benchmark. See, my slides are a bit janky, sorry about that. We incorporated this Penny Lane benchmark into the student cluster competition as one of the challenges. So now we're putting this workflow into practice with our guinea pigs, the students. So what they did is they had to become familiar with GitHub. So this is also a bit of a problem that we found, is if you go overseas or here or try to benchmark what other students are doing at the level of high school and early undergraduate, they've already mastered GitHub. GitHub is something that they do in high school at GitOps. But I mean, the beauty of it is that there's so much information available, and it's so easy to teach that our students, they learned this in a relatively short amount of time, and now we're even at the point where, in this current round, they're committing pull requests to our content to improve it. But going back to the workflow, we started them off in GitHub. We introduced them to the OpenStack Cloud. We had them set up their virtual environments and work remotely through Jupyter Labs, and we had them solving problems in Penny Lane. That was done all on Sabo's OpenStack Cloud. Now, in person, they have physical hardware, and they're actually building and deploying these small-scale clusters and running actual quantum computing problems on these clusters. And not only that, they're scaling them across their clusters to leverage as many qubits as they can in simulation. So what we gave them was a computational chemistry problem that's built up and solved using quantum computing gates. And the really interesting thing in terms of HPC is that you actually have HPC applications that do the same thing. Now, what does that mean? It means that we can have a quantum computing simulation that runs on HPC, and we can benchmark that against actual HPC, classical HPC computational chemistry applications, and just compare those results and see which one does better. Well, we're still not at the point of quantum advantage, but we are getting close. And anyone that's used these SDKs know that it's a simple thing of changing one line. It's you say QML device equals, and you give it your API key, and you can access an actual quantum device. So unfortunately, we're not able to disclose the current status of the work that we are, or the supply that we are trying to secure. But I'd like to think that before the end of the year, or very early into next year, we should be able to provide our quantum computing users with actual access to quantum computing hardware. And not only that, but we'd also like to give our classical HPC users a segue into how they can leverage quantum computing for their day-to-day activities and day-to-day research. So just to cover and summarize the workflow, we have a user, they log into OpenStack, they use that as a sandbox. Once they've appropriately scaled their problem up, they can then move that over to HPC and exploit GPU clusters and GPU resources. Once they've reached the capacity or limits of what they can do on an HPC system, then we're going to allow them to then submit their jobs to an actual quantum computing device. So the main thing here is that we want to encourage collaboration. The quantum computing community is quite small, and the classical HPC users that are prepared to switch over into quantum computing is even smaller. So it's important that we actually share and collaborate and make sure that everyone has access to whatever you're working on, but obviously understanding that people want to publish and they want to be first to publish. So what's important is that keep it private, and once you've completed your work, then just make it available for everyone to reproduce your results. So now, where does this all lead, and why are we doing it? So as we've expressed, is that quantum computing can solve challenges and tasks that current and existing HPC systems are not able to solve in finite time. So if you look at the Sustainable Development Goals of the UN, they want to eliminate poverty, they want to eliminate hunger, they want everyone to have good health and good well-being, quality education, gender equality. I mean, every one of these 17 points is a crisis for South Africa. So we have to start thinking big, and we have to start thinking, I know that Prevalent mentioned multidisciplinary, but a term that Francesco coined, which I really like, is undisciplinary. We can't look at disciplines and silos. We have to say that let's tear down the disciplines, and we have to look at these grand challenges and how we're going to approach them and how we're going to solve them. And especially these 17 from the UN, because each one of these, I think we'd score critical as South Africa. But on the positive side is what we do have as a resource is that if you look at the population under the age of 15, it's right now is you have Asia sitting at around 1 billion of children under the age of 15, and Africa, which is on an increase, they're sitting at around 500 million. So this is the resource. And I mean, this is why I love leveraging our guinea pigs from the student cluster competition to test some of these workflows and test how quickly these things can be adopted and implemented and utilized. So this is where we are going to leverage and maintain our advantage if we can garner one. And it's simply because the youth, they love technology. They love new shiny things, and they're the ones that are going to be coming up to the solutions to those 17 UN Sustainable Goals. So I'd love us to paint the continent orange in the colors of the CHPC and Nikki's and the CSIR. I think this workflow for cloud, HPC, and quantum computing is going to establish Nikki's and the CHPC as a hub. And to quote Max Dupree, the first responsibility of a leader is to define reality. We need to understand the challenges and set our goals and establish where we're going. The last is to say thank you. And in between, a leader is a servant. And as Nikki's, we are a servant to our clients and our users. And hopefully we can continue to serve them and provide them with quality cloud, HPC, and cloud infrastructure. Thank you.